Okay, so today we're going to observe light beams and learn how lenses affect light. So Beckham's putting some batteries in, and then Sterling and Archer, why don't you guys start assembling this? Now we need to go to a dark place. So we're gonna head down to the family room. Okay, so now we're downstairs in a dark room. And can you guys see the beam moving through the air?
Yes.
Can you?
No, you see the red dot.
That's right. You can only see the light spot where the beam stops. Remember the shape the light spot makes when there is no obstacle in front of the laser. What is that shape? There's a circle. Okay. The beam can pass not only through the air, but also through transparent objects. So what does the word transparent mean?
Clear.
Clear or see-through. So look right here. I have a cylinder that's transparent. What do you think will happen when I put this cylinder in front of our laser?
Okay, either it's gonna lie.
Any hypothesis?
Beam everywhere or nothing will happen. Nothing will happen.
What do you think, Beckham?
I think it will just go through it.
Okay, it might change that. So remember, what shape is that you see?
Circle.
And can you see the laser through the air or only where it stops?
Oh, you're gonna hit in the air?
Okay, let's try. We're gonna change the path of the beam. Ready?
It turns into a line.
Ooh!
And the dot on the container.
It's going to fill this up with some water. You are going to unscrew that red lid on top.
Be careful. There's nothing in it.
And we're gonna see how water can influence it. So just a transparent object influence the laser beam. And Sterling, go ahead and fill that pipette up with some water and slowly put some into the cylinder. And observe how this setup changes the path of the beam and affects the light spot on the wall. Mercer, good. Are you watching the wall? See what's happening?
Nothing happened.
Okay, let's see. He's going to add some more water. I don't think the water's quite high enough yet. Keep going, Sterling. Look!
It's a longer line.
Wow!
Make it really long by putting more in it.
I think that's enough, Sterling, since...
No, guys, it's only 5 foot line. It's not gonna get longer.
Yep, okay. So, what did the spot look like initially before we had anything in front of it? Just a little dot. And then what happened when we put a transparent object in front of it?
It became a line.
Uh-huh. And then what happened when we added water?
It became longer.
Very good. Bert, can we see the actual path of the laser? But do you think it's there?
Yeah, it's there. How is that big?
Okay, so you know it's there. We just can't see it. So now we're going to do something to make this path of the ray visible. So in my hand right here, I have some glitter. Okay? And what we're going to do is glitter has lots of small reflective obstacles. And we're going to put 2 drops into our water. And then we'll put our water in front and see what happens. So Beckham's gonna put 2 drops of glitter into that water that we have. You can get it open. So he's gonna pour 2 drops. No, in here, honey. Yep. 1. Did you do 2? Okay. Okay, so now we have our glitter, and you are going to put the glitter in front of this. Right in front of it. Okay, now look on top of that. Can you see the beam now?
Yeah, but it's up high now.
Look at that.
Yeah.
If you look right above it from the top, you can see the beam, the light beam.
And it's really
Don't get it in your eye.
Oh, yeah, but we don't look at lasers, okay?
It makes you go blind so you can't see out of your eye.
Do you see it? How you can see the path from above?
Yeah.
Very
But
cool.
the reason it goes up is because it reflects up.
Along the thin line where the beam is
You don't
shining,
spill the water.
you can see how the particles are moving in the solution.
Where can you take
This
the
is
water?
called the laser sheet method.
Yeah, you
So we're gonna move it forward 30 centimeters very carefully.
Is it supposed to make a reflection on the ground?
Be careful when you're moving it.
Like good? How far?
Now
is
look
it?
in there. Oh. What do you notice about the light beam?
It's like
It's
thicker.
Yeah,
It's
it's
thicker,
thicker.
but not as bright in one place.
So it's a little bit farther away. You
Oh,
can
and
see that
there's a
it's getting
line.
thicker, right?
Yeah, because the water gets. Is that how thick it is?
Mercer.
Fast fact. Here you used a laser, a device that shines a narrow beam of light rays in one direction. Turns out that transparent objects not only transmit light, but also change its direction. Light rays bend when they pass from one medium, air, to another, glass or water. This phenomenon is called refraction. Due to refraction, the light spot turns into a line when you place the transparent cylinder in the path of the beam. Let's talk about how this happens. Before encountering the cylinder, all the rays were going in one direction. Then they bend twice when they enter the cylinder and when they exit it. In total, the rays are refracted in a way that makes them gather together behind the cylinder and then diverge to the sides, spreading like the feathers on a hand fan. To visualize the light's path, one can use a suspension containing tiny reflective particles. As they pass through it, the rays are reflected by the particles that they meet along the way. The reflected rays reach our eyes, which is how we see the path of the beam. From the side, it seems that the laser is cutting the glass of liquid like a knife. Round, transparent objects that change the direction of light beams are called lenses. A set card is a lens made up of many small, cylindrical lenses. Observe on the screen how they change the direction of the beam. So go ahead, Mercer, put that lenticular lens in front of the beam. Can you turn it this way, please?
Okay, and then.
Oh, ho, ho, ho.
You do it like this. No,
You have verified that the lenticular lens changes the direction of the laser beam like a cylindrical lens. The change in the direction of the rays passing through the lens leads to unusual visual effects. And now we're going to check them out using crossed popsicle sticks. Okay, so now we have some popsicle sticks on here. And then you're gonna go ahead and pick up the laser, Beckham. And Archer, you can hold this. You're gonna hold it over top like this. And then Beckham, you're gonna hold that on top and see what happens.
It makes a line.
That's very cool. Now turn it another way.
For
He
me,
has to turn it.
You turn it, Archer.
for me, I can see one popsicle stick. I
Wow.
can see the edge of that. Now you can only. And then what? You can only see one popsicle stick.
Now our question is, can a lenticular lens change a picture's color?
Oh, here
We're
we
gonna
go.
put some stickers on. Transparent objects that have a rounded side and can change the direction of light rays are called lenses. They can have various shapes. The glass in the first experiment has a cylindrical form, so it's a cylindrical lens. You've seen how it changed a laser beam. The transparent plate from the kit is also a lens containing a large number of small cylindrical lenses. When you look at the picture through the plate, the rays reflected from it pass through the plate and on each small lens form small copies of the whole picture the size of the lens. Many small elongated squares are formed on the lens very close to each other, However, our eyes cannot distinguish them, so it seems that the squares from the same line merge into a strip. So how does the lens make the popsicle stick disappear, like Archer noticed? When the stick and lens are located so the vertical popsicle stick is replicated in all the small lenses, the replicas are so small that our eyes cannot distinguish them. This makes the popsicle stick invisible to us. But if you rotate the popsicle stick, the horizontal stick will be replicated, and our eyes can distinguish those replicas. This renders the popsicle stick visible. Such a lens is called a lenticular lens. So what's happening?
Looks like they're connecting them. Let's try the other one now.
Okay.
Now, let's see if I go a little bit
Oh,
forward.
yeah, there we go. It does.
It makes it like a rainbow.
That is really cool. Look at, I can keep going the whole way down. It looks like they're connected.
Yeah. Right.
See that?
Like right about here, it looks the best.
You like that? Okay, now try it down the greens and see if it just makes a long line of greens.
No, the other way down the green.
Mm-hmm. There you go.
A marble.
Oh, that is so cool.
It is cool.
They're at like angle. You don't see it when it's touching.
Right.
You hold it up like right here. You can see the whole thing.
Oh, really? And is it all a big blur?
No, you can see a bunch of green lines and one weird line.
Oh, yeah. So this time we are going to put some opaque particles on the lens. So we're going to add 3 spoonfuls of oat flour to our water and then put it into our cylinder. So we need 3 spoonfuls. 1.
There we go, Emily. Oh, there you go.
That's one.
So nice. Oh, yeah.
One more.
Good job. And go ahead and give it a gentle stir.
Ooh, that's
Oh.
disgusting. Oh, I don't know what oat flour is.
It's exactly what it sounds like it is.
Oh,
Oh, that was not good enough.
it's mixed up oats.
Yep, you need enough in there that it's tall enough for the laser beam to go through.
And then
Here, Beckham. Good, that's, oh, good job. Look what happened now. Can you even see the laser over there?
No, the oat flour is too murky. It doesn't
You freaking oat.
That's
And what if I
right.
do this?
So we,
It doesn't even do anything if I do this.
look at that. It just looks like a little light now, huh? It's completely blocking it.
I know, isn't that so cool?
Do you want to zoom in on the laser's point? In the first experiment, use the transparent cylinder to reveal the line of the light's path. Its round sides stretched out the light spot in a line. If you want to stretch the spot in all directions, you'll need a transparent object that is rounded on all sides, a transparent sphere. When the light beam passes through the sphere, its rays refract at the borders in such a way that they gather at one spot behind the ball, and then diverge in all directions. This widens the beam and the light spot grows. When you pour the oat flour suspension on the sphere, the oat flour particles stop the rays that hit them, casting shadows behind them. The shadows are bigger than the flour particles because the rays diverge and magnify the dark spot. The same way, a small object can cause a large shadow if it is located close to the light source.